Welcome back again, and in this lecture we are going to talk about the LC oscillations, inductor capacitor oscillations. And we have a circuit like this, as shown. I have a KR switch, and initially what we do is we charge our capacitor through a battery, so that the charge on the positive plate of the capacitor is, you can't name them as positive and negative plates, but this plate here, as shown, has a charge plus QM and matching charge minus QM. Okay, and we make this connection here at what we defined as t is equal to 0. Okay. Now, if you look at KVL, Kirchhoff's voltage law, then Q upon C over here, and minus LdI dt, which is obtained by the Faraday-Lenz law, here, this is equal to 0, and the circuit is complete. So over the circuit, we get Q upon C minus LdI dt is equal to 0, where I is equal to minus dq dt. Okay, purposely I have put this minus sign in different color just to emphasize it. So I can write Q upon C plus, because this is di dt will become equal to d2q upon dt2 multiplied by L, and this sign becomes positive over here. This is equal to 0. Okay. So this equation I can write as d2q upon dt2 is equal to minus 1 upon LC into Q. Okay. Now look at this equation, and recall there is an equation like this in the oscillation of springs, or in what is called a simple harmonic oscillator. d2x upon dt2, which is the acceleration, is equal to minus omega square minus omega naught square. This is a positive constant multiplied by x, which is the displacement, which shows that the acceleration is proportional to the displacement and is opposite to the displacement. Okay, this is the definition of simple harmonic motion. And then from here I can write this equation as d2q upon dt2 is equal to minus omega naught square. Okay, again omega naught has been taken with different colors, so minus omega naught square q, where omega naught square is equal to 1 upon LC. L is positive, C is positive, so omega naught square is positive. So omega naught becomes equal to under root of 1 upon under root of LC, and the frequency, angular frequency, the frequency of nu naught is equal to 1 upon 2 pi LC. You know all those things, need not. Like in the case of springs, the oscillation of the springs, omega naught square is equal to Km, and nu naught is equal to 1 upon 2 pi under root of K over M. So there is an analogy that exists. Okay. So let's write the charge on a capacitor as we choose it as Q is equal to Qm cos of omega naught t plus phi. Okay, where phi is the phase constant or the initial phase, and Qm is the maximum charge. Okay. Now we can see as to what is the initial phase or the phase constant, and then we have a condition, a boundary condition, that Q is equal to Qm at t is equal to 0. Q is equal to Qm at t is equal to 0, which has been shown over here in this case. Okay. So, which leads us, if I put t is equal to 0, then I get Qm into cos of phi. Okay, and this cos of phi has to be equal to 1. So therefore phi becomes equal to 0. So this is basically the definition of the time that emerges in the equations. And I can write therefore that phi is equal to 0, so Q becomes equal to Qm cos of omega naught t. And when we differentiate this equation and write the value of I is equal to minus dq over dt is equal to Qm omega naught, and cos of omega t, when differentiated, will give you omega naught into sine of into minus times sine of omega naught t, and so it becomes equal to plus Qm omega naught sine of omega t. Normally we write this as Im, and Im is equal to Qm omega naught, so I get this equation as Im sine of omega t. Okay, so we have the oscillations. This circuit is oscillating with the frequency nu naught is equal to 1 upon 2 pi under root of LC. Okay, now what is there? How it happens? What changes are taking place? So initially I can say that if so, initially, now what happens? If the capacitor is charged, like it has been shown over here initially, when there is no current, then we'll get this as 1 upon CV square, where V is the maximum voltage over here, and this is what is called the electrostatic this thing. As it starts, then the charge moves like this, and the charges on the capacitor become less and less and less and less until this current over here becomes maximum. When the current becomes equal to maximum, then the total energy now it becomes equal to I half LIM square, max square. Okay, and there is no energy left here in the capacitor, and the charge is moving over. So now this starts getting charged, and this plate will become positive and this plate will definitely become negative. Okay, until it is charged fully positive and this is negative. When again the charges they move like this, the current takes the reverse direction, and we get the value I is equal to Im sine of omega t. Okay, now this thing goes on and we have the oscillations occurring. In an ideal condition, the oscillations keep on happening and the energies they transfer from the capacitor to the inductor, from inductor to the capacitor, one after the other. But this is not a proper cup of tea. What actually is there, that this inductor has got a resistance associated with it. Okay, resistance, as I told you, is a Raja beta. So any current passing through it, there is I square R heating, and that will go out. So naturally the magnitude of the oscillations, there will be a kind of a damping. This is one possibility of loss of energy in this kind of a oscillation. There is another possibility. Even if we take that, okay, there is no resistance associated with this system, but the charges are moving. The charges are moving, they may be accelerated, and as we will learn in the due course of time, a couple of lectures away from today's lecture, this lecture, that there are electromagnetic waves, and these electromagnetic waves are generated over here and they are propagated from here in the atmosphere, and in doing so this is the energy becomes less and less, and the oscillations may die out. But as is the case in the case of the swinging a string, so what we have to do is that when the swing is with a natural vibration, natural oscillation, and its energy becomes less and less and less. So we have to provide from outside and force it. We have to give them a package of energy, which again converts itself into the requisite kinetic energy and the potential energy associated with it, so that whatever is being lost is compensated by us. This is exactly the kind of thing that we have in the case of LC oscillation. Okay, LC oscillators have to be fed, of course, the natural frequency of the LC oscillator over here and the frequency which feeds to it, they must kind of match. So once again, the energy over here, this goes like this, the charge over here becomes equal to 0, and then it again goes back, this charge becomes positive and this charge becomes negative, and it is again a build-up. So every quarter cycle there is a build-up. And I tell you that in most of the textbooks of various books, they explain as to what happens after every quarter of a cycle, T by 4, 2T by 4, 3T by 4, 4T by 4, etc. Okay, and they also compare that with the oscillations of a spring in the case of mechanical vibrations. So mechanical vibrations, mechanical oscillations and electromagnetic oscillations which are occurring over here, they have an equivalence, and the books, they take pride in telling you what part is equivalent to what part is equivalent to what part, so you can get and check and obtain a table for that. This is tricky, and whenever the thing is tricky, it requires labor on our part, so we have to read it very slowly, very coolly, and then understand how these oscillations occur. One more thing what you can do is very simple. Okay, you can do the current here is sine of omega naught t, and the corresponding voltage, you can write it as voltage is equal to Vm cos of omega naught t. Why? Because the same C everywhere. So Q upon C. So C is a constant, it's not changing, hopefully. Okay. Then the voltage is there, cosine of omega naught t, and the current is there, sine of omega naught t, and so you can draw the time diagrams and see how the things are changing. Okay. Compare that. You draw the time diagram, one will go sine function like this and the other will come as a cos function like this, and then you can make comparisons at different levels and you understand things fully. So the next item, what I am going to talk to you about, I am not going to talk to you about the damping of oscillations, because this I will take it along with the damped oscillations in the case of simple harmonic motion, plus this at the end of our discussions, because it's a little cumbersome. Okay, and also forced oscillations we'll talk about at that time, but before that I want to finish the course. These are the things. This is a very simple and very interesting and very fascinating thing that is called LC oscillations. Okay, so LC oscillations, what I get, the frequency omega naught is equal to 1 upon under root LC, and nu naught is equal to 1 upon 2 pi LC. T naught will turn out to be equal to 2 pi under root LC, etc., etc. There are many examples available. Okay, and you must do that numerically also you should be able to see as what is the corresponding angle to different cosines, this, that. And of course, in this case, there is no source. Okay? I've just tapped it to show you that it begins a simple LC circuit, it gives out oscillations. So, for today, for now, with the promise that you will draw this curve and see the correspondence between the two of them, and also this maximum energy over here is half CVm square, and the maximum energy here is half Lim square. So magnetic energy converted into electric energy converted magnetic energy, this, that, this. Okay, so it goes on and on and on and on. Of course, theoretically. Practically, the amplitude of the oscillations will, like this or like this, they will die out eventually. So we have to look at that and see what measures we can take. There are measures which are available, but I don't want to tax you at this stage. So thank you very much. Next we are coming up with the beautiful transformers which change the. So Henry was great. Thank you very much.